Hi everybody, Professor Jamer here. So today we're going to be talking about forces. And so today we're kind of just going over what kind of forces can exist and essentially how to start diagramming these forces and how to actually create a force diagram. So let's first talk about forces. So basically all of physics is based off of forces and the fundamental concept of a force. So a force is based off of a push or a pull. So if we have this diagram to the right where we have this girl pulling on a box with a rope, we have many forces in play. So if she wasn't pulling on the rope, we would still have the force of gravity, and then we would have the force of the floor exerting it onto the box because the box isn't moving. But when she grabs that rope, she causes an imbalance of forces that essentially causes the box to move. So if the box moves with some sort of acceleration, we have a net force. And so we have Newton's second law, which is the basis of physics 1 and 2. F net is equal to the mass times the acceleration. So in this case, if the box is accelerating, this physics student pulling on the box is causing a net force through the rope. So overall, we're going to treat everything in terms of vectors because we also have the force due to gravity pulling on the box, and then we have the force that the floor is pushing onto the box that's keeping it static in the y-axis. But whenever we're drawing that force, we're going to draw it from the center of the object, and so this is going to be the normal force. So this is essentially the force that the ground is acting on the box, but we're just drawing it from the center dot. So every physical force has an agent. So while this physics student is pulling on the box with a rope, the rope is here actually the agent. So she's the one actually pulling it, but she's pulling it using the rope, so the rope is the agent. So in the second case, we have a spring, and the spring is an agent. So we know that a spring has a compressive force. So if we had a slinky, which is essentially a spring, and we were to stretch it out, we would know that there's some sort of force whenever the slinky is taut. And it would be a compressive force because if you were to elongate the slinky enough and then you would let go, it would spring itself back. And so the spring would always like to be in equilibrium, but we'll get to that a little bit later. And then here we have the box just free falling. And the reason why it is being pulled down is the force of gravity. So here Earth is the agent. So while the Earth is a physical object and it doesn't have a direct tether to the object, it is causing the force of gravity. So let's talk about the gravitational force, Fg. So here we can always calculate the force due to gravity as the mass times the gravitational constant of whatever planet you're on. So in this case, Fg is pointing downwards since we know the box is being pulled towards Earth. So we can always write Fg is equal to mass times the gravitational acceleration. The next force is the spring force. So if we were to pull the block out from the spring, then essentially the spring is going to be pulling back. So the spring always acts opposite to the actual impetus of the box being pulled out. So we can say that F spring is going to be equal to minus K times delta X, where delta X is going to be equal to X minus X naught, where this X naught is the equilibrium length. Because we know that the spring has some sort of inherent length, and so whenever we are pulling on it, we have to subtract out the spring's original length, and so that's what X naught actually signifies. And so if I have a case where I have a spring and I pull the block out using an applied force, then the spring force is going to point directly back. It's going to want to pull the block back in. So that is why we have that little negative sign in the spring force. So this is also known as Hooke's law for those of you who have previously taken physics. And there's a couple interesting stories about Hooke and how he investigated cork and was able to find this compressive force. So next on our physical forces list is tension, which is essentially if we have a rope, we have a string, we have something that we're being pulled on. And so in this case, our tension force is being applied at an angle. And so normally when we have a tension force, we can apply the tension with respect to an angle. So most of the time we're going to have an X component and a Y component. And so if we are looking at the tension force with respect to the horizontal, Tx is going to be equal to T, the magnitude of the tension, cosine theta, and then Ty is going to be the magnitude of the tension, sine theta. So in a lot of these problems, you're going to have to split up the tension with respect to components. And it's not going to be trivial in the Y component most of the time. So whenever you have the tension force, you're going to always have to consider the Y component. The next one is the normal force, which is essentially if we have a book resting on the table, it is the force that the table has on the book. So if we were to look at this system, so this is my table and this is my book. So I know that the book has a mass, it has a gravitational pull, so I know that there's a gravitational force with respect to that book. I know that the table, if the book is not moving, is going to have an equal and opposite force that's keeping the book from moving. But again, we always draw our vectors with respect to the center dot. So this normal force, which the book calls little n, so I'll use that notation, n is the normal force. And whenever we don't have any acceleration or the block isn't moving or the book isn't moving, whatever it is, then the normal force is going to be equal to the gravitational force. So the next physical force that we're going to talk about is friction. And so we know friction opposes the motion. So if we have a kid on a sled here, so we know that the coefficient of friction between the sled and the snow is going to be relatively small, but it still exists. So the friction, whenever we have kinetic friction opposes the motion of the object. But we also have something called static friction. So here we have a frog, and so he also has some weight. So this is going to be his force due to gravity, pointed directly down. So the static friction is going to keep the frog from sliding down. So whenever the frog isn't moving, he has static friction. And we'll talk about that in a couple more topics, but essentially it prevents the slipping of the frog from moving down the incline. The next force is the drag force, which is basically like the friction of the sky. So it's air resistance. So we know that whenever we are throwing a ball or we're in a plane, that there's going to be some resistance to that motion. And so we call that force drag right here. But we'll talk about that in topic 20, but it's just good to get a good baseline for what all the forces are that we're going to be talking about in the course. The last force that we're going to be talking about in this class is thrust. So basically it's sort of kind of only to deal with rockets or whenever you're propelling something upwards, then we're going to have thrust. So in this case, thrust is pointed directly upwards. It's opposing the force of gravity of the rocket so that it accelerates our rocket upwards. So we have an acceleration vector pointing up. And so whenever we have a system, we have to always draw a picture. So whenever you're solving these problems, the first step is to notice what forces you have and pull them from the bank, the force bank that you have. And you'll have to always diagram all the forces and the directions that they're going in. Otherwise, it is impossible to do these problems. So we diagram the physical forces of a diagram. And this is an example right here where we have the normal force, we have the force due to gravity, thrust, and F net. And we have to figure out the directions that they're in order to set up our equations. And we'll use F net is equal to the mass times the acceleration. So this is Newton's second law, and you'll be using this throughout Physics 1 and Physics 2. So while we just went over all the forces that we have in terms of our force bank, let's do an example problem where we're not too concerned about the names of forces, but we have to efficiently balance them in order to solve problems. So I'm going to switch to the notepad. And so we have problem 1. So in problem 1, we have a 7 kilogram object experiencing 3 forces. We have 30 newtons along the positive x, 40 newtons directed 27 degrees off of the positive y-axis, and then we have 50 newtons along the negative y-axis. And we want to calculate the components of the object's acceleration. So what do we need to do? Well, first, let's write out what we know. That's the first step. So we have an object with a mass of 7 kilograms. We have our first force that is positive 30 newtons in the I hat direction only. Our second force has a magnitude of 40 newtons at an angle of 27 degrees with respect to the y-axis, second quadrant. And then we have F3 that's going to be 50 newtons along the negative y. So we know it's going to be negative 50 j hat newtons. So now let's just draw a quick diagram so this way we can see how the forces balance. So right at the center, we're going to put our mass, M, and then we're going to start drawing our forces. So first we have positive 30 newtons. So this is F1. The second force we have is going to be in the second quadrant. So this is F2. This is going to be 27 degrees. And then our third force is going to be only in the negative y direction. So this is F3. So now we want to split it up into x and y components. So how do we actually set this up? So we know that F net is equal to the mass times the acceleration. So if we were to look at this just in terms of vectors, we would have F1 plus F2 plus F3 is equal to the mass times the acceleration. But we have x and y components of the vectors, so what do we do? So we have to look at the problem with the x component and the y component. So in the x component, I have F1x plus F2x plus F3x is equal to the mass times the acceleration of x. For the y component, I have F1y plus F2y plus F3y is equal to MAY. So here I see that F1 has a x component of 30, since it's only in the I direction. But then for my force 2, I have to figure it out. So here I can see that F2x is going to be related to the sine of 27. So F2x is going to be 40 sine 27, since that leg for F2x is opposite of that 27-degree angle. And then F2y is going to be equal to 40 cosine 27 degrees. So then I say that it's going to be 40 sine 27 degrees, but then I realize I forgot to take into effect that it's in the negative x component, and so I remedy that. So that's really going to be negative 40 sine 27 degrees on both sides. So then this plus becomes a minus, since I'm acting in the negative x quadrant. And so that's going to be equal to the mass. The mass is 7 kilograms times the acceleration of x. And then I can do the same thing for the y component. So I don't have any y component in F1. It only exists in the x component. F2y, I have 40 cosine 27 degrees. And then F3 is equal to minus 50, since it's only acting in the j component, times 7 times ay. So now it becomes an algebra problem, and when I plug everything into my calculator, I get ax is going to be equal to 1.7 meters per second squared, and then ay is going to be negative 2.1 meters per second squared. And so these are my two components, which I can leave in its final form since it's asking me what is the components of this object's acceleration, or I can write it as the acceleration is equal to 1.7 I hat minus 2.1 j hat meters per second squared. So now the next problem. I have an 8 kilogram object and it experiences the three forces. I have 50 newtons directed along the positive y, 20 newtons directed, this is supposed to be 27 degrees, directed, this is supposed to be 27 degrees above the negative x-axis, and 100 newtons directed along the positive x. Expressed as a magnitude and a direction, what is this object's acceleration? So here I have the mass is equal to 8 kilograms. I have F1 is going to be equal to 50 newtons in the positive j hat direction. I have F2 is going to be equal to a magnitude of 20 newtons at 27 degrees above the negative x-axis, and then F3 is going to be equal to 100 newtons directed along the positive x-axis. So now our next step is to draw a picture of these forces to see how they act together. So in the center we have our mass m. I can say that here I have, this is going to be F1, or no, this is going to be F3 because it's 100 newtons in the I hat direction. Here I'm going to have F1. I'll just draw half of F3 for relative scale. So this is going to be F1. And then I have F2 is going to be 20 newtons. At 27 degrees above the x-axis. So now, again, I know that F net is equal to mass times the acceleration. So here I have F1 plus F2 plus F3 is going to be equal to the mass times the acceleration. So now again, I split it into components. So my x component and my y component. So F1 is in the j hat, F2 is going to have 2 components. So for F2, x, I have 20 times cosine 27. And I can say that it's going to be negative since it's in the negative x direction. F2y, I have 20 sine 27 degrees. And I can make my little triangle to prove myself that the y is going to be corresponding to sine because it's opposite to that angle. So now I have f1x plus f2x plus f3x is going to be equal to mass times ax. Similarly, for the y component, I have f1y plus f2y plus f3y is equal to may. So here I can see that for my f1, I don't have an x component, it only exists in j. But I do have an f2x and an f3x component. So then I have negative 20 cosine 27 degrees plus F3 is 100 newtons, and that's going to be equal to 8 times AX since our mass is 8. And I get an acceleration here of 10.3 meters per second squared in the X direction. So for the Y, I do have F1Y. It only exists in the Y, plus 20 sine 27 degrees. I don't have any Y component in F3, and so that's going to be equal to 8 times AY. So here I have AY is going to be equal to 7.4 meters per second squared. So if I were to draw out the direction of my acceleration, it's going to be in the first quadrant. So this is my acceleration right here, and I want to put the angle in terms of the positive x-axis. So my magnitude for my acceleration is going to be equal to ax squared plus ay squared, and I take the square root, and so that's going to be the square root of 10.3 squared plus 7.4 squared. And so that's going to be 12.7 meters per second squared. And then I can find that angle theta because I have AY and AX, so I can use the inverse tangent. So then I have theta is equal to the inverse tangent of AY divided by AX. So that's going to be the inverse tangent, or arc tangent is the equivalent, 7.4 divided by 10.3, and so that is going to be equal to 35.7 degrees. So whenever I talk about it in terms of magnitude, it's going to be 12.7 meters per second squared, and then theta is equal to 35.7 degrees above the positive x-axis based on this drawing up here. So this is essentially topic 14. You're going to see problems similar in the worksheet and also in the homework, so please be prepared to do this work on forces and splitting everything up into components and using Newton's second law, F is equal to ma, and we can go deeper into everything in topic 15. Thanks so much for paying attention, and let me know if you need any help with anything.